Hello learners, welcome to today's lesson. Today we are going to look at a question in chemistry, form 4 under energy changes. But before we look at this question, if you have just come across this channel for the first time, kindly subscribe. Let us read the question together. The setup below was used by a group of form 4 students in an experiment. The readings of the balance before and after the experiment were 10.5 grams and 1.0 grams respectively. Given that the initial temperature and the final temperature of water were 26.7 degrees Celsius and 28.0 degrees Celsius respectively, the specific heat capacity of the water is given as 4200 joules per kg per Kelvin. This is the setup here. We have 50 centimeter cubic of water whose density is 1 gram per centimeter cubic. Then we are heating the water using ethanol as the fuel. The question given is determine the temperature change that occurred, the amount of ethanol used, moles of ethanol used, amount of heat gained by the water, and lastly we have the molar enthalpy of combustion of ethanol. In this case, the information regarding this question has been given. The first question that we are supposed to do is to determine the temperature change. So the solution or the working to this question, looking at the working, to get the temperature change in temperature will be equal to the final temperature minus the initial temperature. And in this case, the final temperature has been given as 28.0 degrees Celsius and the initial temperature as 26.7 degrees Celsius. So if you take 28 as our final temperature, 0.0 minus, we have 26.7. This one is going to give us 1.3 degrees Celsius, and that is the answer to the first part of the question, which requires us to determine the temperature change that occurred. Then B, we are supposed to determine the amount of ethanol used. To determine the amount of ethanol used, initially we had 10.5 grams, and at the end of the experiment we have only 1 gram that is remaining, meaning the difference is what has been used. So to get mass of ethanol used, will be equal to 10.5 grams minus 1.0, which gives us 9.5 grams. The mass of ethanol used would be 9.5 grams. Going to part C. Part C is about the moles of ethanol used. How do we calculate the number of moles? To get the number of moles, we take the mass of ethanol that was burnt over the relative molecular mass of ethanol. In this case, the mass of ethanol is 9.5 grams. We divide by the molar mass of ethanol, and in this case, the molar mass of ethanol is 46 grams. How did we get 46 grams? We know ethanol, C2H5OH, the relative atomic mass of carbon is 12, but we have 2, that is 24, plus the relative atomic mass of hydrogen is 1 times 6 hydrogens, that will give us 6 plus. The relative atomic mass of oxygen is 16, giving us 46. In this case now, to get the number of moles, you take 9.5, you divide by 46, which is the relative molecular mass or formula mass of ethanol, and that gives us 0.20652 moles. That gives us 0.20652 moles of ethanol used. Then D, it is the amount of heat gained by the water. That is like the heat change. So that is our D. Heat gained or heat lost in that matter will be given by the mass of the water. We multiply by the specific heat capacity of the water times the change in temperature, which we have already calculated in part A of this question. So the mass of the water will be 50 grams. Why? We are heating 50 centimeter cubic of water with a density of 1 gram per centimeter cubic, meaning if you want to get the mass, you take the volume, you multiply by the density, and that will give us the mass. So the mass is 50 grams. You divide by 1000 into kilograms. We multiply by the specific heat capacity is 4200. It has already been given. It is 4200. Then you multiply by the change in temperature, which is 1.3. And if you work out this question, we have 50 divided by 100 times 4200 times 1.3, and this gives us 273 kilojoules. That is kilojoules, because energy is measured in joules or kilojoules since the mass has been converted into kilograms. Another question that we have is the molar enthalpy of combustion of ethanol. We want to find out the amount of heat energy that would be given out if 1 mole of ethanol was burned. But we know when 0.2, that is part E, when 0.20652 moles of ethanol were burned, this amount of energy was given out. That is 273 kilojoules were given out. What if we burnt 1 mole of ethanol? This one would be 1 mole times 273. We divide by 0.20652, and this one will give us, divide by 0.20652, and this will give us 13. This will give us 1321.9. This will give us 1321.9 kilojoules per mole. And since this reaction involved the evolution of heat, therefore we are going to introduce that negative there, meaning the reaction was exothermic. Another question we have, part F. Use the following thermochemical process to answer the questions that follow. We have propane being burnt to give us 3 moles of carbon dioxide and 4 moles of water with the evolution of 125 kilojoules per mole. Then we have carbon alone. When you burn carbon in air, it gives you carbon dioxide, and the heat involved is negative 393 kilojoules per mole. And again, when you burn 1 mole of hydrogen, you get negative 286 kilojoules per mole. So Roman 1, draw an energy level diagram representing the formation and the combustion process of propane, carbon, and hydrogen. So when we talk about an energy level diagram, this is a diagram that shows the relative energies of the products and those of the reactants. Now, with the energy level diagram, we are going to have F part 1. This is the energy change. Then of course here we are going to have the reaction progress or the reaction path. We know that the entire process is exothermic, and therefore the products are going to be lower than the reactants. So we are going to begin by number 1. We are going to form propane, and for us to form propane, that is C3H8, we are going to require 3 moles of carbon plus 4 moles of hydrogen. So for you to form propane, you need 3 moles of carbon and 4 moles of hydrogen to give us what we call propane, which is C3H8. So this one is the enthalpy heat change of formation of propane. Then from there now, you can burn. If you burn propane, any time you burn a hydrocarbon or an organic compound, it will give us carbon 4 oxide and water. And we have been given, if you burn propane in air, it will give you 3 moles of carbon 4 oxide. You get 3 moles of carbon 4 oxide, which is a gas, plus 4 moles of water. 4 moles of water. So if you burn propane in air, it will give us carbon 4 oxide and water. And for us to get carbon 4 oxide, it is the same as burning. It is the same as burning carbon directly in air to give us carbon 4 oxide. And for us to get water, it is like burning hydrogen directly in air to give us water. In this case, if you do that, you would have drawn the energy level diagram, that is for the formation of propane and that of combustion of the same propane together with carbon and that of hydrogen. Here now we can say this is the heat change of combustion, and we are talking about the heat change of combustion of C3H8. Going down to the question. The question again says, Roman 2, hence or otherwise determine the heat change of formation of propane. To determine the heat change of a substance, we know the heat change is always on the forward process. So the enthalpy heat change of formation of propane, which is C3H8, will be equal to the difference between the enthalpy heat change of combustion of carbon plus that of hydrogen minus that of burning propane directly will give us the enthalpy heat change of formation of propane. In this case, the enthalpy heat change of combustion of carbon alone, 1 mole of carbon requires or gives out negative 383. So we take negative 393 kilojoules, but we are burning 3 moles, so we multiply by 3 plus 1 mole of hydrogen will give us 1 mole of hydrogen will give us negative 286, but we burned 4 of them. We minus that of burning propane directly in air, which is negative 125. In this case, this is the enthalpy heat change of combustion of carbon alone, then that of hydrogen, then we minus that of burning propane directly. The difference will give us the enthalpy heat change of formation of propane. In this case now, we are going to have negative 393 times 3 plus we have negative 286 times 4, and this gives us negative 2323. We minus negative 125, minus is like a plus, and this one will give us negative, that is plus 125, and this gives us negative 2198 kilojoules per mole. We can confirm this. That is negative 393 times 3 and that is the answer to Roman 2 of part F, negative 2198 kilojoules per mole, and that is the enthalpy heat change of formation of propane.